Good day. This is Bob Norcross of Norcross Corporation, here to present to those who are viewing it the Sensitivity Challenge. Primarily this is aimed at those of you who are printers, flexogravure, coders of numerous types, and laminators. It's a challenge to consider what kind of eFlux cup are you using? Is it really working for you? Is it really showing you what's happening in your process? Do you really know what's happening in your process? I want you to think about this. Ponder and learn as we go through these following slides. I want to challenge you to think outside the box, to look for the invisible, to bring the invisible to light and make it obvious, to improve your processes and make your production more efficient, more beneficial, and make your company more competitive. Thank you. I hope you enjoy this presentation. So who are we to make this challenge? We're a company established in 1946. Over 3 generations of experience in the world of process viscosity control. We have and do work in over 30 industries. We have over 30 different control systems. We also provide customized control systems. We understand that Centerpoise is not Centerpoise. You can ask more about that in a separate presentation. We are established around the globe, active through many sales channels. We're qualified to issue this challenge. Are you able to rise to the challenge? Norcross Corporation is the only viscosity control company in the world with one specialty and mission: to improve your process viscosity control process. We've been doing this only for 80 years. Norcross Corporation was there when flexographic printing was invented. We work on central impression, inline, and stack presses. We can be used on solvent-based inks, water-based inks, epoxy inks, gold, silver, and adhesives for laminating. Only the Norcross sensor can be used across this wide gamut of liquids without any change in our sensor technology or our controller. We have been there. We are there. We know what the story is. Gravure printing. We were there in the 50s on publication gravure. We're there today on packaging gravure. We understand gravure. We know about gravure. We're there. Laminating. The gluing together of 2 sheets of film, or film to metal, or metal to paper, or film to paper. We are there on both solvent-based and water-based adhesives. We can measure them. We have experience with them. Corrugated printing is preceded by making of the corrugating, which itself is preceded by making the corrugating glue. We operate both in the glue kitchen, in the corrugating adhesive application line, and now as printing on corrugating is pushing new boundaries. We measure the viscosity and pH of water-based corrugating printing inks. These and many other applications we have ongoing experience with: printing on golf balls, syringe coating, PCB manufacturing, conformal coatings of final PCB assemblies, making of wire enamel in chemical reactors, coating wire and coating transformer windings, making all types of glue and the use thereof, and laminating. Norcross covers the world. In 80 years of existence, we've sold in most all parts of the world. Currently active in those areas shown. We're based in Boston. but we understand the unique needs, requirements, and desires of each country we enter. We respect your desires, your needs, and seek to bring to you benefits, efficiencies, and understanding of just what viscosity is and how to control it. We have shared with you who we are, what we have done, where we have been, what we know. We trust you will now accept the challenge to grasp a hold of your sensitivity. Not doing so is costing you efficiency. It's harming the workers. It's harming the environment. And it's just wasting your resources and money. This is not necessary. It's often very easy to correct. But when you talk about sensitivity, one often says, "What's the accuracy?" That is the wrong question. Accuracy is a function of one's calibration. There is no absolute viscosity for a non-Newtonian fluid, which all the applications I've talked about deal with. It's the sensitivity you worry about first. Can you see small changes in viscosity, such as here the red chart shows a changing viscosity of water from 100 C down to 14 C. This chart was drawn with a reading taken every minute over the course of almost 24 hours. This shows sensitivity and repeatability. You bring your process to where you want it, and then we keep you there. The first arrow shows the viscosity at 100 degrees C. The second black arrow at 14 C. There's almost a threefold change in viscosity. No other process viscometer can draw this chart. No, not one. This sensitivity, combined with our simplicity and ruggedness, gives exceptional performance, enduring life, and ease of operation. So we come to a question. Does the cup you are using really work? Does it show you changes in viscosity? You may think it does when it really doesn't, and I'm going to show you that as we go forward in this presentation. Some cups are very sensitive. Some have almost no sensitivity. You may think you're measuring viscosity. I might say you're not. Or if you are, you're measuring with such poor sensitivity, you could be off by 20, 30, 40, 50% in your viscosity and not even know it. Today's machines don't want to work like that. To optimize your machine, you have to optimize your viscosity. You can no longer afford to live with a cup that doesn't show you changes in viscosity. There are many cups in use around the world, and this list is just a partial list. Some cups are named for people like the Zahn, some for institutions like the DIN and the ISO, others for companies like the Ford, Iwata, and Shell. There are many other cups, too many to list. Most cups share a common lack of sensitivity. They don't show you what is really in the glass jar in terms of changes in viscosity. There are a few cups, the Shell being one, that can show you the changes in viscosity that the other cups do not show you. This is sensitivity. This is where you start to see the invisible, where the invisible becomes obvious. So then you can take control of your process and improve your process and succeed. During the course of my life in doing process viscosity control and traveling all around the world, so often I hear, a cup is a cup. We've always used this Zahn cup. Well, everyone else uses them. It is good enough after all. These are not true. This is a false message. You need to move beyond. If you want to achieve true progress in your process control, and receive the benefits thereof. You may be asking still, Bob, what are you saying? Well, I hope not, because I'm talking about sensitivity. It is reasonable for you to ask, why should I care? And that answer is coming. But first we have to further explain sensitivity and why the Zoncup lacks sensitivity. Sensitivity is seeing the change in viscosity of water as its temperature changes, which then means you can see fine changes in viscosity of inks, coatings, adhesives. And the falling piston simply crushes the Zoncup when it comes to sensitivity. Let us now consider the number 2 Zoncup at 20 seconds. At 20 seconds, the viscosity is approximately 30 centipoise. Now with the Zoncup, you can measure it plus or minus 1 second at best. As shown here, this means the viscosity could be anywhere between plus or minus 13% of the 30 centipoise. That's a spread of 8 centipoise, or a gross spread of 26%. When you measure with the Zoncup, you have no idea where you are within this spread. You just don't. Now, let's consider the shell 3. The steeper slope tells us that it's more sensitive. The sharper cutoff lets us read to plus or minus 0.5 seconds. This equates to a spread of 1.5 centipoise. That's a gross spread of 5%, down from 26%. Now you're able to start to see those changes in viscosity which are invisible to a Zon-type cup. You need to see the invisible and make it obvious. Then you can begin to control it. Here we have a Zon 3 at 20 seconds. You'll notice at 20 seconds the viscosity is approximately 130 centipoise. Now, as said before, the Zoncup can be measured at plus or minus 1 second at best. This results in a range of 14%, 20 centipoise, or plus and minus 7% from the 130. Again, as said before, this means when you measure with this Zoncup, you don't know where you are within a spread of 14%. Now let's consider the shell 4. The shell 4 is more sensitive and also has a more clear cutoff, thus you can read it within plus or minus 0.5 seconds. With this cup, your span is only 5 centipoise, a total of 4%, plus or minus 2%. Again, now you can see changes you cannot see with a Zoncup. You need to see these to deal with the newer machinery and the process quality improvement that your customers are demanding. We're now looking at the last cup in this presentation, the Zon 4 at 11 seconds. 11 seconds is approximately 100 centipoise. This is very approximate because 11 seconds is below the useful range of any efflux cup. Yet this is a real-world situation that actually has been encountered. Therefore, it's something you should be aware of and understand. At 11 seconds, your spread is 28%, meaning when you use a cup like this, your viscosity could be anywhere within a 28% spread of your desired viscosity, and you cannot see where you really are. Now let's look at a shell 4. The steeper incline indicates more sensitivity, as said before in prior slides. It has a plus or minus 0.5 second resolution, unlike the Zon at plus or minus 0.1 at best. This results in a 6 centipoise or 6% spread, plus or minus 3. Thus, with the Shell 4, you can begin to see what the Zon is totally unable to show you. You need to make the invisible visible, or you can't deal with it, but it will deal with you. It is my hope that by now you might be asking, just why is a Shell cup different than a Zon cup? Before you see some high-speed photographs, which even in real time can be replicated and observed. The first point to note, the Zon cup's design results in an unclear cutoff, a dribbling at the end, i.e., you, the human with a stopwatch, are trying to guess when to stop the stopwatch. So the unclearness of the drain time termination, combined with your human reflexes, results in this plus or minus 1 second at best cup reading value. The Shell cup has a different design at the end of its orifice, resulting in a much sharper cutoff, which therefore gives it this plus or minus half a second resolution for measuring its drain time. And the steeper slope, i.e. increased sensitivity, is caused by the longer orifice. It's applying more shear. The fluid has to flow through a longer pathway, and viscosity is a function of shear. If you apply more shear, you can see the changes more easily. This is the reason the Shell cup, or any cup with longer orifices, are more sensitive than those cups with very short orifices. Sometimes I'm asked why, if the longer orifice cups are better, why do people keep using the short orifice cups? The answer is tradition. The Zon cup was created when my grandfather created the first process viscometer. Back then, the resolution and sensitivity of the Zon cup was fine. The machines were simpler, running slower. Solvent loss, ink loss, coating loss weren't so critical. Thickness of coatings or adhesive layers weren't so critical. But times have changed, technology has changed, machines have changed. But way too often I see people still using an outdated method of checking their viscosity. It simply continues to hide the invisible, which has to be made obvious. You cannot live with something hiding your viscosity changes. So with the foregoing explanation, I now ask you, is your cup a friend or a foe? Is your cup a tool for value and efficiency? Or is it leading you deceptively to waste? You may be totally innocent and ignorant of this. It doesn't change the fact. The wrong cup is your foe. The right cup is your friend. It will lead you to a better operation, and today's world is growing smaller and smaller. And those of you who want to succeed and proceed into the future, you have to keep up with the machine technology, the quality technology, and if you're using the wrong dip cup, the wrong efflux cup, you're not going to make it. We are about to come to some slides showing the difference between manual control and automatic control. For even with a good efflux cup, manual control is still insufficient, inadequate, and not appropriate. The cup helps you begin to see the unseen truth. A good process viscometer completes seeing and then controlling. When you can see the invisible by bringing focus to your eyes, then you can find a pathway forward and design control systems and procedures to take advantage of the right equipment and therefore maximize the use of your machines. Minimize the use of your coatings, your solvents, and your inks. All these things work in your favor. It's a win-win-win. The truth of manual versus automatic control. The truth that some understand and follow, that some understand but choose not to follow, and some do not understand. This chart recording is a real live situation on a real printing press. The first section shows the variations in viscosity, 3 cup seconds on a Zahn cup when in manual control. Point A is where they begin the process and adjust the viscosity. So it's about 50 on the chart. The operator goes off to do some of the work and comes back later and takes a reading. The viscosity obviously increases due to solvent loss. He adds some solvent manually and drives it down. Goes away and comes back again. The zigzag is huge. The wasted ink and wasted solvent are huge. The threat to quality is immense. You might have ink too thick and your color may hold, but if he over-dilutes, your color will not hold. That generates scrap and waste. When you go to automatic control, suddenly these variations evaporate. Good automatic control can result in ink and solvent savings. We've seen numbers from 10 to 50%. It depends on your prior or existing condition, and it depends on how well you implement the control system, how well you mix the ink, and how well you train the operators not to do as in point J, where a large amount of uncut ink was added to the ink tank, driving the viscosity off the chart. But with auto control, it quickly brought the viscosity back to within range and restored the quality. Once you stabilize the viscosity, you can then actually begin to reduce the viscosity down to the minimum level required to maintain color intensity. At this point, you're maximizing your saving by minimizing the film thickness applied, be it ink, adhesive, coating, paint. You want to minimize your film thickness to what is acceptable. There's no sense in shipping extra material out the door. Here is another chart on an actual rotogravure press in China. You can see the section of manual control. The viscosity varies up and down, up and down. They add solvent, they add ink. They respond to measurements with their dip cup. You can then see where the automatic control engages and how fine it holds the viscosity. So fine you cannot measure it with the normal efflux cup. You cannot see the changes because the Norcross falling piston sees the invisible. It makes it obvious. Therefore it can deal with it. It can control it, and you can benefit from it therefore. We have spent some time discussing the differences in efflux cups and why they are different. We've shared information regarding manual versus automatic control and the astounding dramatic differences. Yes, even if you run a short run of 30 minutes, you should be using viscosity control. Longer runs, it's even more obvious you should be using viscosity control. I've given you some illustrations. If you cannot see something, you cannot measure it. If you cannot measure it, then you cannot control it. We're now going to proceed to talk about one example that illustrates how the falling piston sees the invisible and controls the invisible by first making it obvious. We're now going to talk about the falling piston. In front of you is a chart used in the prior example of the Zahn 4 at 11 seconds, with a 100 centipoise set point. We have to make a few changes in this chart, since the falling piston measures time of fall with a resolution of 0.1 seconds. So I'm blocking out the left vertical axis and creating a right vertical axis. Assuming the piston is falling in 5 seconds at the 100 centipoise, with a resolution of plus or minus 0.1, that equates to a resolution of plus or minus 2 centipoise. This is extremely fine measuring of change in viscosity. And being done automatically, it results in the incredible improvement in stabilizing viscosity as opposed to manually measuring with a Shell or a Zahn. Even though the Shell is much better than the Zahn and will give you better control, the automation of it is what you really have to move towards. For even with the Shell cup, the falling piston can control viscosity so fine, the Shell cup may not even see it, and the Zahn cup has no prayer of ever seeing it. When it comes to automatic control systems, we offer first various types of plug-and-play, standalone systems, easy to bring in, quick to set up, and quick to get operating. Some customers prefer these and might have one for each station they're doing. Other customers prefer to mount the controllers in their own panels. We have single station controllers and two station controllers. They can be mounted in a panel and used to control the sensors on the ink tanks or even in the ink line. And then other customers desire multi-station touchscreens with trend plots, such as the VISC shown here, which does 10 stations. The choice is yours. We're now 2 slides from the end of the presentation. I've given you the information. I've shown you the evidence. The choice is now yours. You've listened. But can you act? Can you choose? Are you able to see what I've tried to explain to you and move forward, to experiment, to develop your processes, to take advantage of seeing the small changes in viscosity, which do impact your process, do impact your quality, and do cost you money, and will make you less competitive? Or do you just want to shrug, sit back, and stay as you've been? Let the invisible stay invisible, and enjoy the darkness that it brings and has brought to you. I can't force a thing upon you. I've presented you this information to enlighten you, inform you, and give you a choice. It's your choice. It's your decision. Norcross is here to serve. We look forward to hearing from those of you who want to move ahead. Welcome to the next to last slide. The last slide has some technical information you may be interested in and does not have me speaking, so listening is almost over. 2 last points we want to make. The first is a real-life story. Turkey, Istanbul, 2007. Flexographic printer doing a trial of our falling piston viscometer. He's run the same job multiple times using 100 kilos of ink each time he runs the job under manual control, using a Zahn-type cup and a stick to stir the ink. We get our equipment up and running, turn things on, get him going, he runs the job. The job goes just fine, the color holds, the number of meters run is the same. The job works fine. They finish the job, take away the roll, turn around, and there's 40 kilos of ink still sitting on the floor. They said, okay, we believe. 40% ink savings. We have witnessed this firsthand. Last point, we have one mission: to improve your viscosity control. We touch in pH for corrugators, but our One main mission is viscosity process control and has been for 80 years. We understand the non-Newtonian thixotropic shear-sensitive nature of fluids. We know where we cannot go. We know where we can go. We know how to guide you, coach you, and help you. That's our desire. Thank you for listening, and have a good day.